hi everybody. This is the second part of Gauss's law, chapter 22. So it's 2.2. Last time, 1.9 should be changed to 2.1. Okay, now in this example, we are now considering a solid non-conductor like billiard ball. Somehow the charges are homogeneously distributed within the volume. Okay, for plastics, we can do this. For instance, we can put some nanoparticles, charged nanoparticles, in this melt non-conductor, maybe plastic or something like that, and then cool it so that it has some kind of shape like that. Not necessarily spherical, okay? But if we have a good mixture, these positively charged nanoparticles will be hanging within the body, and then now we can consider this charge distribution. Although the total system is solid, we can calculate the electric field distribution within this charge distribution and outside, okay? So it means that if radius is r, we will just get the electric field when r is less than capital R, which is the radius of the system, which happens to be spherical in this case. But what is the electric field line when r is greater than r? Or equal to, okay? Equal to, we have to use this equal sign because the electric field here at this point should be continuous, okay? So the electric field that you find from this, okay, or just on the left, will be equal to electric field line you find from this part just outside. So the electric field lines will be continuous. So although there will be some kind of this sharp point, okay, the electric field will be just changing its direction abruptly, but still it will be continuous. So okay, so our objective is to find what is the electric field for this homogeneously distributed, okay, homogeneously distributed charges. Okay, so we will do this. But before solving this, let me tell you something. If you have metal shell, which is just the shell, inside is empty, doesn't matter the shape, or you have the solid metal, for instance, steel ball. So it's all metal everywhere, okay? It's solid metal, okay? In this case, if you just touch this by something which is positively charged, remember that we learned in the very first part of our lectures, then you can just transfer these charges, and then the total surface is automatically loaded by positive charges, okay? So if you remove this rod, then the total the charges will be distributed evenly on the surface, and then the total surface will be negatively charged. But do you know, actually what's happening is this: although this is a thin metal shell, it is a thickness. Where are these plus charges coming from? Okay, remember that these plus charges came from the rod that we touched over here. In this case, do you know what happened? As soon as this rod touched the surface, at any point, doesn't matter, the metal electrons just realize that there is some positive charges, okay? So that, suppose that the thickness is this, although it's thin, but still it will have a thickness, So what will happen is that, because now, remember that when we remove this earlier, before touching this surface, earlier, the surface metal shell was neutral, but now all of a sudden outside is positive, then the electrons will just move to overcome this problem inside. So inside surface will be coated by negative charges. But the thickness, you know, this is happening in a very small amount of thickness, okay? So now this metal shell is again have no total. If you just get a little piece like that, the total charge is zero. So the electrons are so dynamic, okay? So because there are positive charges, then on the other side, mirror image is mirror charges just are happening, and then they are gathering so that we have now plus and minus there. So there will be some electric field within this little thin shell, but usually we just ignore the thickness of this shell so that we don't really observe this phenomena. So this is just something that I've told you, but we will probably not getting into the details and look into the skin properties of this little metal shell. So for this one, the charges are totally positively distributed. They came from outside, okay? But what about this solid metal? If you again touch this by a positively charged rod, and only the surfaces are accommodating the charges. So inside, within the volume, there is no charge. So there is no way that the electrons will be moving within the body. The electrons only will move on the surface, okay? On the surface. But you can only put the charges on the surface, not inside. So if you choose a Gaussian surface inside here, of course, our Gaussian surface for this case will be spherical. And here, as you see, because it's empty, no charge. This is Gaussian surface again. No charge in Gaussian surface. Here also, if we choose the Gaussian surface again, we have no charge in the Gaussian surface. In this case, for these two cases inside, okay, suppose this is R and this is R again, the same, suppose that we have a spherical case with the same radii. In this case, because there is no charge in Gaussian surface, the flux, which is EDA, okay, will be equal to Q enclosed over epsilon 0, remember? But this is equal to 0, so that it's 0 totally. No flux, no electric flux. Okay? No electric flux. In this case, if we use this to solve electric field, we say that the result is that electric field is equal to 0 inside shell, metallic shell, or solid metal. Okay? Electric field is always 0. This is very nice, especially when it is empty, because this is now called Faraday's cage. And electric field inside Faraday's cage will be totally 0. Whatever is happening outside, maybe there are some lightnings or maybe very high amount of charges are distributed, or some cosmic rays are coming or something. Doesn't matter. Inside, still electric field is 0. Very nice. So this is a very good opportunity. We use this in physics, okay? Many devices are designed within this metallic shell so that outside effects are totally eliminated. Of course, the electric effects for this case. We will see that later. If it is totally closed, and there is no way that the magnetic fields will also diffuse inside. So both electric and magnetic fields will be 0 inside the Faraday's cage, okay? The magnetic field will also be 0. And then this is an excellent opportunity. If you are dealing with some wave propagation, some or something, you always do this experiment within the metal shell. Sometimes we do plasma experiments and oscillations and gas, charged gas things, experiments. In this case, you also cover yourself with the metal shell. Otherwise, this high frequency oscillations will behave like an antenna. And then if there is a little hole, they will just diffuse outside and just propagate outside. So these signals will propagate outside if there is a little hole here, which we don't want usually. Okay, now, so having stated this very important property, so we solve this problem. In this problem, don't forget, okay, we have even distributed charges, which is not physically possible and technologically very difficult, because you will have very small nanoparticles, maybe positively charged, and you are melting this plastic in a shape, and then you mix and then just solidify and get this shape, and you can just hold it with your hands like that, and the charges will have been distributed evenly, but not able to move at all. But in metals, as you see, if there is a little bit effect, these charges just move around. But here, just these charges are just hanging there. Okay, they just stay in their position. Okay, now this is an interesting example, although not very physical, and probably not too many applications of this in real life. But we will assume two cases. One, when the radius is smaller than the radius of the ball, okay, non-conductor, or when the radius is greater than that. So let's do this case first, okay? So when the radius is smaller than or equal to r, the electric field is now solved. Okay, so Gaussian surface is this. So this we choose the Gaussian surface. Let's draw this shape again, okay? Don't forget, they have equal distances to each other. And then this is the center, and now we draw our Gaussian surface inside, okay? And then we say that this is small r, although the total radius of the system is just capital R. Don't forget, we are only choosing r, which is smaller than capital R. Of course, this case covers the whole volume just inside of this shell, okay? When r is less than or equal to r. Now, don't forget, this is the Gaussian surface, and if the radius is r, so we are now solving this, right? E dA as Q. Okay, so if you just add all these charges, it gives you total charge. Sum of the charges included. Obviously, some of the charges are included. Okay, but now what we know is that if you draw a surface area vector, okay, it's dA, because we are in spherical geometry. But now if you draw the electric field lines also parallel to dA, E parallel to dA. In this case, theta is 0 degrees and cosine theta is 1. Wow, this is good, because we know that this was carefully chosen as a Gaussian surface, which really simulates the total structure, which happens to be spherical in this case, okay? So in this case, this is just 1, and what we know also is that if r is constant, which is the case, because the Gaussian, on any point on the Gaussian surface, r is constant, electric field is constant, okay? So you can take it outside. This is why we chose it, because we're solving the electric field inside. So electric field is constant, and now electric field is constant. This is 1, this is equal to 1, so that all we are left with is E dA is equal to Q enclosed over epsilon 0. But now this is 4 pi r squared, but small r squared, because we are dealing with the Gaussian surface. Capital R is the limit of R. Don't forget. Now this is a variable. Variable R is changing from 0 to capital R. So it's equal to right hand side, Q enclosed over epsilon 0. So the electric field is found if Q enclosed is solved. But Q enclosed is sum of the charges, not all the charge. So this is not equal to Q, right? Because it's only some portion of it. Okay, so how can we do this? We can use proportionality, okay? So we say that the total volume, which is 4 pi, 4 over 3 pi, because this is a volumetric distribution, right? Volumetric distribution. This is a three-dimensional shape. That's why we have to compare the volumes. So the total volume 4 over 3 pi r cube includes Q, but our little volume with the Gaussian surface 4 over 3 pi small r cube is having Q enclosed. Very simple. Proportionality. So we use cross product, right? This is how we do it. 4 3 pi r cube times Q enclosed will be equal to this product. So main diagonal, off diagonal. Okay? So 4 over 3 pi small r cube times just Q. So as you see, 4 over 3 pi's will cancel each other, and then Q enclosed is given as just simply r cube over capital R cube Q, total charge. We know that Q enclosed is smaller than total charge because we just considered only a portion of it. Obviously, this must be correct. Is this correct in this expression? Yes, because capital R is always greater than small r. So that this expression, this expression is always less than 1. So it's okay. It's correct because we can only have a small portion of the charges. So now when put this into this expression, then E times 4 pi r square will be equal to, okay, Q enclosed over epsilon 0. Let's put the epsilon 0 there. And now Q enclosed is just r cube over capital R cube. Okay, just Q, total charge. Okay, now we solve the electric field. So inside, electric field is given by, again, 1 over 4 pi epsilon 0, which is K. Now this, as you see, r square cancels r square on the right-hand side, and we are left with just r. Okay, it's just r over r cubed, okay, times Q. Q is written here. So basically, this is the electric field inside. What's happening? Electric field is linearly changing, okay, inside. And I will just graph it later on. Okay, so but what about outside? So this is the first part. The first part is finished. Electric field is a function of radius. So if you go from this point to that point, you measure R and insert here, electric field intensity is found. So whatever the coefficient is increasing, as you see. So electric field at R equals 0. Now what we learned is that at R equals 0, electric field is 0. Right in the center, there is no electric field because center is just a point and it doesn't have any dimension. And obviously, we expect no electric field if there is no, if the size of the Gaussian surface is almost negligible. Okay, so it means that you're just making it smaller and smaller and smaller. This Gaussian surface will include no charge in the center. Okay, in the limit. So this is the part that we have solved. Just inside it is no electric field because R is 0. When you put R is 0 there. But what about the surface though? What about surface? If you insert R equals R, then it's the surface electric field. Now let's put R there. So E equals Q over 4 pi epsilon 0. Now this R over R cubed, okay, when you cancel that, R squared. So it's just K Q over R squared. Wow, you know, we just found the same result. Excellent. This is what we expected. This is exactly the same value that we have to find when you are solving outside also. Okay, good. Now what about outside? What about when R is greater than or equal to capital R? In this case, let's draw the shape, regular shape. Again, there are many charges hanging in this solid billiard ball, and the total charge is Q, by the way. Okay. Now our Gaussian surface is not inside but outside here. Now our small r is this, and the area vectors are that. Okay. And electric field line. Now, what's happening? We are outside the total shape. Then we have to consider the electric field lines starting from the surface, which is obviously outside because everything is spherically symmetric. So that the electric field lines, again, from this positively charged ball surface, doesn't matter now it is metal or not, will be given in this direction. And they are all parallel, as you see, E parallel to dA again. Now we are solving, we are applying this Faraday's law. And cosine theta is 1 again, as before, right? It's just a larger area. So this is our Gaussian area. Okay, let's put the name Gaussian area. In this case, now we have E dA again. E is taken outside, is equal to Q enclosed over epsilon 0. But in this problem, Q enclosed is very simple because the total charge enclosed is just Q, because we are enclosing all the charges. So we're not dealing with a region, but the total charge, which is Q. Very simple. And this is 4 pi r squared. Then electric field is just, okay, 1 over 4 pi epsilon 0 Q over r squared. Wow, it's very interesting. Because when we set R equals R, okay, when R equals R, we end up with the same thing, K Q over capital R squared, and we have the same thing. So it means that we are okay, because we solve the electric field inside the body, we solve outside, but right on the surface, the electric field happens to be exactly the same, which should be. Otherwise, there is a problem, okay? You're making a mistake, okay? Now, let's graph this case. Volumetric charge distribution, okay? Let's graph. How do we graph this electric field line as a function of R? Of course, R should start from 0, okay? This is the electric field as a function of R, okay? We know the direction, that's why we're just graphing the magnitude. And let's say that this capital R, the radius of the total ball. So until this equation is valid. So for this part, the electric field is just K Q R over R cubed. But for this part, electric field is just K Q over R squared. Okay? So now what happens is that this is linear dependence. It's like Y equals mx, linear line. In this case, we don't have x but r, and this slope is just this. This is slope, right? This is slope. Slope is kq over r cubed, and it goes linearly to some value. What is this value on the surface? Very simple. We found it right there. It's just this, kq over capital R squared. Okay? But now, from this again, this is correct. We have 1 over r squared dependence, so it's just decaying. So the function goes down. But it never approaches to 0. It never goes to 0. It approaches 0. Okay? So it means this is long range effect. So although you are so far away from this shape, you will still feel the effect of it. But here, inside electric field is 0. This is a very important part. Electric field is 0. But now, here at this point, electric field is maximum. It's very interesting. The electric field is maximum. So you can solve the electric field, for instance, and get the derivative and set to 0, and then you find this maximum point. But this is a very singular point, though, because if you look at the left part of this point, the slope is this way, which is positive. But if you just look at the right side of the point, the slope is extremely negative and totally perpendicular to the other slope. So slopes do not match. So although it's continuous, it doesn't have any slope here. So it's not easy to get the electric field line by taking the derivative with respect to r and setting to 0, because this is not a continuous function at this point. But everywhere it's okay. Okay? But this is discontinuous. Okay? It's continuous, but doesn't have any slope. Sorry. So the electric field is to be continuous on the surface. So it cannot have a shape like that. Suppose we have like capital R, electric field goes here, and then right after that it drops like that. So there is a discontinuity. There is no way. So this is not physically allowed. Okay? But actually, if you look at the problem very carefully and consider the skin depth of this, okay, we will see that this is actually similar to that. Okay? So if you look at the problem microscopically, suppose that this is the skin depth, okay? The electric field line will be coming like that and probably reduce a little bit and then drop like that. So if you squeeze this region, you can see there is a drop, okay? So if you squeeze this region, suppose that we have like that, okay? So the electric field line will come here and then start dropping like that. So it will look like there is a discontinuity. However, within the metal body, the electric field also will be changing, right? Do you expect this is so? The answer is again no, because there is no electric field, okay? Because this is metal shell, okay? If the metal shell, there is no electric field, but this is plastic, so that it's possible the electric field will change like that. For plastic, okay, plastic, okay, electric field will change like that. But for the metal, okay, for the metal, if the electric field line is coming this way, somehow, we know that electric field is 0 inside the body, but outside, okay, there will be some electric field line going this way, okay? So there will be no discontinuity if you just squeeze this region. But we will see that electric field inside the metal is totally 0. So the electric field will go from 0 to very high jump, very high values, and then it will just jump to this. So for the metal, there is a discontinuity. Okay, there is a discontinuity, okay, okay. For the plastic, the electric field line will change from a maximum value to a smaller value on the surface, but we're not going to be able to detect this difference if this skin depth of this thing is very small, okay? In this case, we're not dealing with the skin depth because it's just a plastic, right? We don't need to investigate the skin depth. But here again, we are assuming that some of the charges just hit the surface and then make the surface charge, and there is no reason that you can consider this one. So basically, for this problem where electric field is changing linearly inside the volume, okay, and then outside it's reducing as 1 over r squared, 1 over r squared. So this is the electric field. Now, if we solve the metal thing, another example, if it is, remember the 3 pictures that I have drawn, this was the first, the second, and the third. So it doesn't matter if it is shell or solid conductor, shell conductor. But now the surface is on the surface, the charge is on the surface plus, and here also the charge on the surface. Okay, the total charge is Q again. Okay, the charges are here. Not necessarily plus, of course. It can also be negative because it's just a habit that we use these plus signs. Okay, so the radius is r. Now, when r is less than r, electric field is 0. But when r is greater than or equal to r, electric field is just given as k q over r squared. Okay, we have solved this earlier. Okay, it doesn't matter if it is point charge or the spherical charge distribution. If this shape is, in this case, the graph for this case, for the metal case, as you see, it's side by side, electric field, this is R, okay? For the conductors, electric field is totally 0 until R, but it just jumps to a value and then starts to reduce like that. Exactly the same dependence. So let's draw this similar to this shape, like that. Okay, so looks like there is a discontinuity in the electric field. What about the electric field here? Again, the same thing. Okay, kq over capital R squared. Okay, electric field at this point is given by this. Okay, good. So we solved the electric field inside the solid or shell conductor to 0, but not 0 in this case if they are evenly distributed. But outside is always the same case. Okay, the expression that you found from Coulomb's law. Okay, so this is the end of today's lecture. We stop recording now, and you can ask